Since 1939, mathematicians have worked on a problem called the Jacobian Conjecture. In July 2026, an announced example gave 3 different inputs the same output. If the formulas hold up, no single undoing rule can recover which input was used, and the conjecture is false in 3 coordinates. In 1998, Stephen Smale placed this problem on a list of 18 important problems for the new century. His list also asked what human minds and computers might be able to solve. Levent Alpoge announced the example. He credited Akhil Mathew with asking the question and a computer system named Fable with producing the example. If that account is accurate, a computer helped find an answer, not merely check one that people had already found. The material shared with the public does not show every search step. Discovery credit is not mathematical evidence. We will build the needed ideas, then check the formulas directly. Start with a familiar number rule. The number 2 goes in. The rule adds 3. The number 5 comes out. We call 2 the input, 5 the output, and the rule a map. A map is just a rule that gives each allowed input exactly one output. To undo this map, start with 5 and subtract 3. That returns the original input, 2. A rule that always recovers the original input is called an inverse. Here, adding 3 and subtracting 3 undo each other. Now change the rule to square the input. Both 2 and -2 produce 4. Can one undoing rule look only at 4 and know which input was used?
No, it cannot. The same output came from 2 different inputs, so the output has lost the information needed to choose between them.
That is exactly right. We will call that meeting a collision. One collision is enough to show that no single inverse works for the whole map. The map receives 3 input coordinates, named with the letter X, the letter Y, and the letter Z. It returns 3 output coordinates. The first output is named with the letter P. The second is named with the letter Q. The third is named with the letter R. Later, we will name 3 exact inputs point A, point B, and point C while their coordinates remain on screen. Here, a polynomial formula may use addition, subtraction, and multiplication. It may also use whole number powers. A variable never appears in a denominator. That operation boundary, not the formula's length, is what makes the formula polynomial. Our map has one polynomial formula for each output coordinate. The first formula produces the output named with the letter P. The second produces the output named with the letter Q. The third produces the output named with the letter R. Together, they make one polynomial map. The Jacobian conjecture is about maps of this kind. Before facing a map with 3 inputs, start with one that has only 2 inputs. Write the letter P beside the first output. Its rule is X plus 2 times Y. Write the letter Q beside the second output. Its rule is 3 times X minus Y. Now change only the first input, named X, by a very small amount. Keep the second input, named Y, still. In the first formula, X appears once, so the first output changes by 1 copy of that small amount. In the second formula, X appears 3 times, so the second output changes by 3 copies of that small amount. Next, change only the second input, named Y, while the first input stays still. The first output changes by 2 copies of that change, and the second output changes by -1 copy. The multiplier connecting the small input change to the immediate output change is called a derivative. When several inputs exist and only one changes, that multiplier is called a partial derivative. Place the results in a table. Each column says which input we changed. Each row says which output we watched. The top left one says how the first output changes when the first input changes. The bottom right negative one says how the second output changes when the second input changes. This table shows how each input immediately changes each output. It is called the Jacobian.
A real map has 3 inputs and 3 outputs, so its table has 3 rows and 3 columns.
Yes, it does. That gives 9 entries. Each entry chooses 1 output to watch and 1 input to change. Return to our example with 2 inputs and 2 outputs. Each of these 4 numbers came from the recipe we just tested. The first column records what happens when x changes a little and y stays still. The first output changes by 1 copy of the x change, and the second output changes by 3 copies. The second column records what happens when y changes a little and x stays still. The first output changes by 2 copies of the y change, and the second output changes by -1 copy. A very small input square has one side made by changing x and another side made by changing y. After the rule acts, the first column tells where the x side goes. It becomes the blue arrow. The second column tells where the y side goes. It becomes the amber arrow. Those 2 arrows are neighboring sides of the new green parallelogram. For a table with 2 rows and 2 columns, the area calculation has a short rule. First, multiply the upper left entry by the lower right entry. Here, 1 times -1 gives -1. Then multiply the upper right entry by the lower left entry. Here, 2 times 3 gives 6. Subtract the second product from the first. -1 minus 6 is -7.
Why does subtracting those 2 products describe area?
If the 2 output arrows fall along the same line, they do not surround any area. In that case, the 2 diagonal products are equal, so the subtraction gives 0. When the arrows do surround a parallelogram, the result tells how the input square's area changed. Ignore the minus sign for a moment. 7 says that the area becomes 7 times as large. The minus sign says that the 2 sides have swapped their order, so the new shape is flipped like a mirror image. This one number is called the determinant. The question we need later is whether the determinant is 0. The determinant tells what happens to a very small square. When the determinant is 0, the square is flattened into a line. It no longer has area, so this immediate change picture cannot be reversed. When the determinant is not 0, the new shape still has both width and height. With 3 coordinate slots, we use a very small box and ask whether it keeps its width, height, and depth. When the determinant is not 0, no immediate change has been completely erased at the chosen point. The inverse function theorem then guarantees that the map can be undone inside a small enough region around that point.
So this promises an undoing rule near one chosen point. It does not yet promise one undoing rule for every point in the whole space.
That is correct. That single word nearby is where the coming puzzle lives. An inverse can work perfectly inside one small region. It can also work perfectly inside a second region far away. Yet both regions might arrive at the same target region. Each small part is undoable by itself, while the whole map cannot tell the 2 parts apart. The conjecture allows complex numbers, written as a plus b times I, where I squared is -1. Real numbers are included, so the 3 real collision points we will use are valid inputs. Here is the full Jacobian conjecture. Start with a polynomial map having the same number of complex input and output coordinates. Suppose its determinant is the same number everywhere and is not 0. The conjecture says the map must have a polynomial inverse, one whole space undoing rule whose coordinate formulas are also polynomials. The claim was meant to hold for every number of coordinates. With one coordinate, the claim is true. A polynomial with the same non-zero derivative everywhere must be a straight line with non-zero slope. Its inverse is another straight-line polynomial. The mystery begins when changing one input can affect several outputs. Now we can ask the real question. The screen shows 3 different inputs, named point A, point B, and point C. Each enters the same polynomial map, which we name with the letter f. The map returns 3 output coordinates. At every possible input, the determinant of the map's Jacobian table is exactly -2. Since -2 is not 0, the inverse function theorem gives an undoing rule near every chosen point. Make a prediction. Can input point A, input point B, and input point C still arrive at one identical output, or does the determinant never becoming 0 make that impossible?
I choose impossible. I know the theorem promises only a nearby inverse, but having that promise at every point still feels as if it should cover the whole space.
That feeling is exactly the leap made by the Jacobian conjecture for polynomial maps. But the announced map sends input point A, input point B, and input point C to the same output point. We name that output point D. The equality on screen records this shared destination. We will now check both facts exactly. The determinant is always -2, and these 3 inputs share one output. Now we inspect the announced formulas themselves. Their source and discovery credit are recorded, but only exact calculations can show whether they work. The combination 1 plus x times y appears repeatedly, so the formulas call it u. This shorter name keeps the next 3 lines readable. We name the first output with the letter p. Its exact polynomial recipe is on screen and will remain available for the checks. The second output, named with the letter q, uses the same short name u. Its exact polynomial recipe is now on screen. The third output is named with the letter r. Together, these 3 displayed formulas completely define the polynomial map. To disprove the conjecture, this map must pass the stated condition and fail the promised result. The first exact check must show that the determinant is always -2. The second must show that 3 genuinely different inputs share one output. These 2 checks settle the question without asking us to trust the difficult search that found the formulas. The first exact check begins with the Jacobian table for our announced map. Its 9 entries are partial derivatives. Each row chooses an output to watch, and each column chooses an input to change. We will calculate one entry by hand. In the third output, only the middle term changes when y changes and x and z stay fixed. Its multiplier is -3 times x squared. Therefore, the partial derivative of the third output with respect to y is -3 times x squared. The complete table now appears one row at a time. The first row watches the first output. The second row watches the second output. The third row watches the third output and contains the entry we just calculated. We need the table as exact evidence, but we do not need to memorize its 9 formulas. First, choose the input where all 3 coordinates are 0. The 9 formulas reduce to the mostly 0 table on screen. This does not prove the condition everywhere. It gives us one clean table on which to see the complete 3x3 determinant calculation. Start with the top row. For each entry, remove its row and column. That leaves a 2x2 table. Multiply the top row entry by the determinant of that smaller table. Then combine the 3 results with the signs plus, minus, plus. Here the first 2 entries are 0, so their contributions vanish. The final entry is 1. It leaves the 2x2 table highlighted on screen. Its determinant is 0 times 0 minus 1 times 2, which is -2. So the determinant is -2 at this particular input. The conjecture requires the same conclusion at every input, not only at the input we chose. A short exact computer program keeps every input coordinate as a variable instead of replacing the coordinates with sample numbers. It calculates all 9 partial derivatives, applies the same 3x3 determinant rule, and combines terms with the same powers. The arithmetic is exact, with no rounded decimals. When terms with the same powers are combined, every term containing an input coordinate cancels exactly. The only remaining term is -2. The complete program is included with the episode sources, so the calculation can be inspected and rerun. The notation on screen now states the full result. The determinant of the Jacobian table for the map named with the letter F is -2 for every input. Every input coordinate remained a variable throughout that calculation. Therefore, the equation holds for every input, not merely for a list of successful test points.
So the map has passed the conjecture's condition. -2 never becomes 0, which gives a nearby inverse at every point. This check alone still does not give one inverse for the whole map.
That is exactly right. The second check asks whether different inputs meet. We will work through input point A, then display the same exact check for input point B and input point C. At input point A, both x and y are 0. That makes u equal to 1 and makes nearly every term disappear. The first output is -1/4. The second and third outputs are 0. For input point B, x times y is -3/2, so u is -1/2. The exact lines on screen leave -1/4 for the first output and 0 for the other two. So point B reaches the same output as point A. For input point C, x is -1 and y is +3/2. Their signs changed, but x times y and the value of u stayed the same. The exact lines again leave -1/4, 0, and 0. Point C reaches the same output too. The equality on screen says that input point A, input point B, and input point C all reach one output point. That output's first coordinate is -1/4, while its other two coordinates are 0. The three inputs are different, but the output is identical. As the squaring example taught us, one shared output makes a single undoing rule impossible.
Now we know both facts. The determinant is always -2, but three inputs share one output. The claim tried to cover every map that passed its condition, but this map passes and still fails the promised result. This map is a counterexample to the Jacobian conjecture.
The inverse function theorem is safe. To see what it does not control, let t be positive and use the input shown on screen. Its first coordinate grows with t, while its other two coordinates shrink as t grows. For every such input, x times y is -1, so u equals 0. Substituting that into the exact recipes gives the output on screen. First coordinate 0, second coordinate 2 divided by t, and third coordinate 0. Now let t grow. We can make the first input coordinate as large as we choose, so the input point runs farther and farther away. At the same time, 2 divided by t becomes closer and closer to 0. The first and third output coordinates stay at 0, while the second output coordinate approaches 0. These inputs can run as far away as we like, while their outputs stay near 0. That is the missing comparison. The determinant describes immediate changes beside one point, not the relation between inputs far apart.
The determinant describes the immediate changes beside a chosen point. It does not compare that point with another input very far away. So an undoing rule can work near every point even though no single undoing rule works for the whole map.
We now have a counterexample with 3 coordinates. Which case do you think is still unsolved? 1 coordinate, 2 coordinates, or 3 and every larger number?
I choose 2 coordinates. We already know the claim is true with 1. Starting from 3, we can add more coordinate slots and copy each new one unchanged.
That is correct. The 1 coordinate claim is proved true. The 2 coordinate claim over complex numbers is still unsolved. The announced example makes the claim false for 3 coordinates, and 1 copying step carries it to every larger number of coordinates. For 4 coordinates, call the extra input w. Use the map that we named with the letter F on the first 3 inputs. Then copy w unchanged into the 4th output. In the new table, the zeros mean double, u does not mix with the old coordinates. The corner one means w is copied without change. So the determinant is the old determinant multiplied by 1. Still -2. We can repeat this copying step for every added slot. Add a 4th coordinate equal to 0 to input point A, input point B, and input point C. Their old outputs already matched, and the new output coordinate is 0 for all three. The collision survives. The same copying step works for every larger number of coordinates. Because this result is extremely new, the careful phrase is announced counterexample. Its support is the two repeatable exact checks. The determinant is always -2, and three inputs share one output. The claim for every number of coordinates is false, but an important question remains. With two complex input coordinates and two complex output coordinates, does a determinant that is the same number everywhere and never zero force one polynomial undoing rule? No proof or counterexample is known yet.